Hello dear students, welcome back to NEET 1. So we are discussing hydrocarbons and we have completed discussion of alkanes here right now. So in the last 3 sessions we have completed till the discussion of alkanes, okay, and we have also started discussion of alkenes. So where we have covered the preparation of alkenes, right? So in this session few more methods to prepare alkenes as well as the chemical properties of alkenes will be discussed, okay. So one of the very important topic here is chemical properties of alkenes, okay. So what are the chemical properties it has? Like there are some reactions like ozonolysis, hydroboration and oxymercuration, demercuration. These are some important reactions to be considered from this particular discussion for your EAPCET, JEE and NEET exams, okay, right. So look at these, we have covered this many things in the last class like Wood's reaction as well as Franklin synthesis, Coriolis synthesis, all these are for preparation of alkanes right now, and we have seen these questions. If you are unable to solve these questions, you can watch our previous discussions, okay, previous live sessions in this channel you can watch, okay. And look at this is a complete conclusion I have given in the last class. Let me check whether voice is clear or not. Right, everything is clear. Right. So here I hope you have seen the last video where we have discussed all these chemical reactions, right. So now here I will be giving the content about alkenes. Like in the last class we have discussed about geometrical isomerism also. So when this geometrical isomerism is possible, so when the given compound is planar, what I am saying, given compound is planar, it means geometrical isomerism is not possible in alkenes. What I am saying, not possible in alkanes, okay, as well as in alkynes also it is not possible. In alkynes also it is not possible, but in alkanes yes it is possible, but in alkanes it is possible. Alkenes, but in alkenes it is possible, okay. Alkenes and alkynes it is not possible, but in alkenes it is possible, okay. As well as cycloalkanes will be there now, like cycloalkanes here. So here I am writing in simple cycloalkane it is not possible, okay. So from number after 8, ring size after 8 it is possible in simple cycloalkanes, but here if it is having any substituents like methyl group is there, here also some methyl group is there, then we can say cis trans isomerism in these cycloalkanes also along with our alkenes. See, so these alkenes show geometrical isomerism because we can place the given substituents either same side in the given plane or in the opposite direction, okay. So here they are in same side of the alkene now, so alkene double bonded carbons you can check here, they are on same side, so you can say it as cis alkene, okay. Now I am placing the methyl groups in opposite direction, like one is above, one is below, this is trans alkene, okay, trans alkene. So generally what we can call 1 2 3 4 now but 2 in now, so cis 2 butene and trans 2 butene you can say. So this is about cis trans isomerism. Now there are some compounds in which both groups, attached groups here are not same. So in that case some example let us take, it is something like this. So at this double bond here it is methyl group, here is some other alkyl group, some propyl group is there. Now how can we identify? So simple here, so we need to give here not cis trans, you can give here EZ. So what is this EZ isomerism? Whenever the attached groups are not same, you need to prioritize the groups here. Out of these two, which is more prioritized group? Methyl group. So this is number 1. Out of these two, which is more prioritized group? This is alkyl one. So this is 1. So how I am giving alkyl group as 1? You just need to follow CIP rules. What it says, wherever we have more atomic number, that will be prioritized first. If atomic number is same, you need to consider mass number. So based on this, so 1 1 are opposite. So in this case, if they are priority groups are on opposite side, you should call it as E, opposite means E, N-tag again. Okay. So next, here they will give something like this. Like this they will mention. Okay. So now in the given compound, how many stereoisomers are possible, they will ask. Now how many double bonds are there here, just check how many double bonds are there. So it is 1 and here it is 2. So 2 double bonds we are seeing now. Now 2 double bonds are there and surrounding, like here what is a group attached, hydrogen and methyl here. And what about this, this is ethyl and 1 hydrogen. So the substituents terminal groups are also different now. So in this case you just use 2 power n, where n indicates number of stereo centers. At this double bond we can say Ez, and at this double bond also we can say Ez. Therefore you can say 2 power 2, that is 4 stereoisomers are possible. So what are the 4 stereoisomers possible? Here also you can write it as Z, here also you can write it as Z. So it can be ZZ, or it can be Z here and there it can be E, or here it can be E, there it can be Z, okay, or both can be EE. So these are the 4 possible stereoisomers for this given molecule. Okay, what is the simple formula? 2 power n, where n indicates number of stereo centers in the given molecule. Okay, like this you need to write. Okay, right. Yeah. Next here, just tell me your answer. Those who are in the live session, just give me your answer for this question. Here I am writing. So tell me number of stereoisomers possible for this. What I told you, just count number of double bonds. At each double bond, just check whether 4 different groups are there or not. It means just on each carbon, whatever the groups attached, that must be differ. Okay, if these 2 groups are same, there is no Ez isomerism at that carbon. Okay, we cannot differentiate them now, we cannot prioritize them now. So whenever there are same groups on the given double bonded carbon, we cannot give Ez isomer, but here they are different. So out of these 2, this is 1, this is 2, like that. Just identify at each double bond, and if the groups attached are different, then we can expect Ez isomers. So how many are possible here? So there are 3 stereo centers now. You can take 2 power 3. Okay, so 2 power 3 means 8. How many stereo centers possible? 8. That's it. This is your answer for the question. Okay, right. Yeah. Then next, after this I just wanted to give some example of cycloalkanes also. So look at this, here I am attaching methyl group, here also methyl group. See how they are, both methyl groups are indicated above the plane. See, this is the indication for above the plane right now. So if both groups are above the plane, what we can say, both groups are on same side, same groups above the plane. So you can say this is cis isomer. Okay, so next, if they are on opposite direction, I mean opposite plane, like one is above the plane, other one is below the plane, then what you can say, this is trans. Okay, these are cycloalkanes. If the cycloalkanes having substituents like above the plane and below the plane, then we can say cis trans isomerism as in this manner. Now just tell me here what I am writing here, cyclobutane I am writing, chlorine, hydrogen, chlorine. Now tell me what is this, is it cis trans, cis or trans? See, chlorine, chlorine below the plane now. So you can say this is cis, same side means cis, opposite side means trans. Okay, right. After this we have preparation of alkenes from alkynes, alkyl halides, vicinal dihalides and alcohols. First of all, you need to understand this basic one first. Alkynes if you take, so alkynes if you take, now upon treating this with sodium or lithium in liquid ammonia, okay, so it will produce in liquid ammonia, it will produce trans alkenes, it will produce trans alkenes or C double bond C or H and H. So how they are trans to each other, alkyl groups are trans to each other. No? So whenever we are treating alkyne with alkali metal like lithium, sodium in liquid ammonia gives trans alkyne. So if the same reaction happens with H2 PD CaCO3 and quinoline, so we are going to get a cis alkene like this. Okay, now what we are seeing here, conversion of alkynes to alkenes. So this is a example of partial reduction reactions. Partial reaction means only one double bond is converted into, one pi bond is converted into sigma bonds, I mean converted into alkene format. It means one double bond is one pi bond is replaced by hydrogen atoms on each carbon right now. So what is the reagent here we are using? Sodium and lithium in liquid ammonia. Okay, so whenever we are using this, we can call this reaction as Bruch reduction. Okay, in this Bruch reduction what happens? One double bond of alkane converts into like alkene format. Okay, you just remove double bond pi bond and you can write it as an alkene, and that particularly trans. One pi bond should be removed here. Okay, trans alkene. Okay, now here if we treat this with this one, we can call this H2PD CaCO3 as a Lindlar's catalyst. What I am saying? Lindlar's catalyst. Okay, so this is called Lindlar's catalyst. So what is the use of Lindlar's catalyst? That converts alkynes to alkenes. Okay, remember this. And here it is cis alkene. What is this? It is a cis alkene. Okay, remember these two reactions. Okay, very very important, these two models for your EAP set. Okay, and the next one here, you just see here what I am doing. From alkyl halides, see, let us take one alkyl halide. See, this is alkyl group. Okay, butane you can say. Here I am placing one halide X. Now whenever you are treating this with alcoholic KOH under heating condition, what happens? What will be the product formed here? This will be the reaction given. So now just see, a halide attached carbon is there, na, that is called alpha carbon, and the adjacent carbons are called beta carbons. So how many beta carbons with respect to halide? So this is beta, this is also beta. So here it is a methyl group and this is an hydrogen atoms here. Now tell me what happens here. What happens here, tell me. So this base, alcoholic KOH, act as a base and that abstracts a proton from here. So this will abstract a proton here. This pi bond, this sigma bond will be converted into pi bond and gives a double bond here. So what is happening here? Halide ion is removed, hydrogen atom from beta position is removed as a proton. Okay, so that it will be making a double bond. Okay, so the same scenario can be happens from this side also, because this is also beta hydrogen now. So you can get one more alkene like this. So these two are possible, A and B, but out of these two, A is major. Why this is major? This is major because it is a more substituted alkene now. So we have studied hyperconjugation where it explains more the number of alpha hydrogens with respect to this double bonded carbons, more is the stability. See, this double bond is in conjugation with 3 alpha hydrogens of this carbon and 3 alpha hydrogens of this side carbon also. Okay, so it means it will be stabilized by 6 hyperconjugative forms. It will be stabilized by 6 hyperconjugative forms. This side 3, there also 3. So therefore 6 times it will be stabilized by hyperconjugations. Okay, so this is one of the important factor to be remembered. Okay, and one more thing here, I am giving you one example. Just tell me, so tell me what is the product formed? Where do you get the double bond again? Where do you get the double bond? Tell me. Yeah, so here you can see CH3 group this side, this is alpha to this, this is alpha, this is beta to the bromide ion. Again this is also hydrogen we have at beta position. Okay, that is also removed with along with this bromine. Okay, so now there are two possibilities, so we can remove this. See, you might be getting why we are only removing beta proton, why not other proton? See, because at alpha position we have bromide ion now, so this is sigma bond. So what is it? It's a sigma star orbital, like this is how sigma star orbital is oriented. So now this sigma star orbital is exactly parallel to the beta proton here, which is trans to this bromide ion. Therefore the trans proton at the beta position is removed along with this bromide ion. Okay, you will get a double bond like this. Okay, and this side also possibility is there, you will get this kind of product. So again, which is more substituted alkene? See, to these, how many alpha protons are there, alpha hydrogens are there? So this side 6 and this side is 3. So total 9 are there. So this is more stabilized. That's why it is formed as major. Okay, we need to remember this concept here. Next one here I am giving you one more example. Here I have a halide ion, like consider it is a bromide or a chloride. Now treating with alcoholic KOH, tell me under heating condition. See, elimination reaction. So what we are removing? We are removing two groups. Now we are eliminating two groups from the starting material. See, one bromide ion, one proton are removed. So from the starting material, when we are converting into this format, we are eliminating one proton and one bromide. So we can say this is an elimination reaction. We are removing the two things. So from the starting material, we are removing two things. It means these elimination reactions are favored by high temperatures. Why high temperatures? So just look at this delta G equation. Delta G equals delta H minus T delta S. Okay. So now what happens is, now higher temperature favors these elimination reactions because it is an endothermic process. Elimination reactions are endothermic process, it means this is positive. Okay, so now in order to make this more negative, so in order to make this more negative, why I am saying more negative? We know already entropy is positive. Okay, so entropy is positive, so negative term is there here. So positive into negative, this is negative. Okay, so we can make it more negative, it means reaction becomes more negative, it means positive. I mean more negative means what happens? I can say it is more spontaneous. Okay, so we can make a reaction more spontaneous by making delta G value more negative. So this is possible by making increment in the temperature. So high temperature favors elimination reactions. What I am saying? Elimination reactions are favored by high temperature. Just remember this condition. Okay, whereas substitution reactions happen at normal temperatures only. Okay, right. So again, what is the base I am using here? Alcoholic base. Like in alcoholic medium, its basic nature will be more, alkoxide ion will be more basic, that's why alcoholic KOH is used. If I use aqueous KOH, that will prefer substitution reaction. This is the effect of solvent. If I use aqueous KOH, what happens? In the place of bromide ion, we will get OH minus. But what I want elimination reactions. It means this group should be removed from here. So it means KOH here we have taken as should act as a base. So for that only alcoholic medium will be preferred, not aqueous, and under heating conditions at high temperatures. Okay. Now what happens here? This is a base. Here we have bromide ion which is attached to this carbon. I am considering it as alpha. These two carbons are beta. Now where the proton will be removed so that the double bond will be generated either here or here. So how can we decide that? Just write the possible products in both cases. If I remove proton from here, we will get a double bond like this by removing this one along with this hydrogen. Okay, and place, and this side also, if you see this side also, here you have a beta proton, so you can remove this beta proton and this bromide ion and you will get a double bond like this. So this is A, this is B. Okay, so which is major here? Which is major out of these two? Tell me, how can you identify that? See, this double bond is in conjugation with the pi electrons of this ring, whereas this double bond is not in conjugation with the pi electrons of the ring. Therefore, what happens if these pi electrons are in conjugation, it will be more stabilized now, because more the number of conjugation, more is the stability. So which alkene is more stable? This alkene is more stable now. So if it is more stable, formed as a major one. Okay, more stable alkenes are formed as major in the reactions. Okay, more stable alkenes forms as major in the reactions. Next, can you answer me for this one last question? Take it as a homework, or you just try on your own and tell me your answer in the comment box. What is the name of the product formed? Tell me, that's it. So what is the name of this major product formed? Just mention its name in the comment box. Identify A, which is major, and tell me in the comment box. I will be looking into it. Very easy. Just use your knowledge that whatever you have learned, what to consider, more stable alkenes are formed as major. Okay, right. Here, one more thing. There is another scenario also, like see, whenever you have very weak leaving group, fluoride ion is very weak leaving group, whereas bromide, chlorides are good leaving groups. Okay, what is the leaving group ability? Leaving group ability is fluorine, chlorine, bromine, iodine if I consider. So bromide ion goes out easily, then iodide ion goes out easily, then next bromide ion, then next chloride, and then next fluoride. So this is the leaving group ability of the attached groups here. So now weak leaving group is fluoride ion. So whenever there is a weak leaving group, okay, upon treating with alcoholic KOH, since it is a weak leaving group, so what happens is elimination of proton from this terminal side. It means less substituted alkenes are formed as major. Okay, in the previous case in our discussion, more substituted alkene is formed as major now. Okay, but whenever we have a very weak leaving group like fluoride ion, elimination of proton takes place from this terminal side and gives this terminal alkenes as major, and our internal alkenes in this case is minor. So this will be minor. So whenever there is a very weak leaving group, okay, not only very weak leaving group, if the leaving group is very bulky, consider here what I am writing. So N CH3 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 I am giving. So tertiary ammonium ion is given, alcoholic KOH under heating condition. Yes, tell me what happens here. There are two possibilities. This is alpha, here beta, here also beta. From where we need to remove proton, tell me now. So there are two possibilities. You can remove from here or from here. Okay, but from where it happens, tell me. So it's a bulky group now. So the base is unable to enter inside. Therefore, it will deprotonate from less substituted or terminal carbon only. So here if I remove, we will get internal alkene, but if I remove here, you will get a terminal. So in this case, whenever there is a bulky leaving group or a very weak leaving group, so we will get less substituted or terminal alkenes as major. Okay, less substituted or terminal alkenes as major. Okay, then next one here is bromine only we have, like good leaving group only we have, but if the eliminating group, I mean if the base taken here is very bulky, tertiary butoxide ion I am taking here, potassium tertiary butoxide I am taking. Okay, so just tell me, this is very bulky, right? This is a very bulky group now. So now what happens? This bulky group will not enter inside of this given alkyl substrate, and it cannot able to deprotonate from this more substituted side. So therefore it is easy for this bulky group to remove proton from less hindered side, and that generates a double bond here. Okay, that's why terminal alkenes formed major whenever the base is bulky. Bulky base is there means you'll get a terminal alkenes like this. Okay, remember these reactions in which the terminal alkenes are forming and in which the internal alkenes are forming as major. Okay, right. Okay, so same thing, alkyl halide we have completed this. Now we have to do the same process with alcohols. So that is previously whatever we discussed, it is from alkyl halides. Now here these are alcohols, hydroxy groups are there, like OH groups are there on alkyl chain, that's it. So now there we have used alcoholic KOH under heating condition. Here we need to use proton like acids. Okay, protic acids will be using a concentrated sulfuric acid or dehydrating agents like P2O5 will be used. Therefore it will dehydrate or it will remove OH from here and a beta proton. So there also beta proton, here also a beta proton is removed, and that will be generating a product. Okay, now how can you get this product? Just look at the mechanism. This is also elimination reaction only. Now these are the suitable reagents preferred here. Sulfuric acid at 160 degrees Celsius, orthophosphoric acid or P2O5 which is a dehydrating agent, or Al2O3 which is a dehydrating agent. Okay, Al2O3 at 350 degrees Celsius, P2O5 under heating condition to be used along with these things. Okay, so now look at this. Here I am writing OH group. Now what happens, tell me? Just treating this with H plus like sulfuric acid at 160 degrees Celsius, consider. Now what happens if I remove this OH group? We will get a positive charge here, that is a secondary alkene which is less stable right now, secondary carbocation less stable. So but beta protons are there now here. So these beta protons will be removed from here like this. Okay, and you will get a internal alkene, and if I remove from this terminal side, we will get terminal alkene. Out of these two, which is major? So internal alkenes are major here. Okay, so A is major. Okay, so how do we get the stability order of alkenes? That is purely on basis of hyperconjugation. Okay, more substituted alkene is more stabilized. Right. Next, after this, look at this reaction. CH2OH is mentioned. So I am writing here sulfuric acid. Okay, at temperature they will mention 160 degrees Celsius. Tell me what happens here. First of all, sulfuric acid releases H plus ion. Okay, that released H plus ion is taken by our OH group, and it will be now taking, after taking H plus ion, it will become cyclohexyl ring. It is CH2 here, it becomes H2O, it will becomes. Okay, so positive charge here. So now if this water goes out, What is the charge creating here? Positive charge. Okay, so now this compound carbocation we got here. So this compound positive charged carbon is primary carbon here if you observe. How many carbons attached to this carbon? Only one now. This is alkyl group only, so primary I can say. So now here you have a beta proton here. So if I eliminate that beta proton, you will get a simple alkene like CH2 double bond here by deprotonation. But if I transfer this proton from here to here by carbocation rearrangement, you can get a CH3 and positive charge here. How this third carbon proton is coming from here to there by hydride shift. So that's why you got a positive charge on this tertiary carbon. So this tertiary carbocation is more stable now than this primary. So that's why rearrangement is taking place. After forming this positive charge, so you just consider the beta protons here. This can be a beta, this can be a beta, this can also be a beta. So both of these are same now. So you can remove one of it, and that will generate a more stable internal alkene. So consider between these two which alkene is more stable. This is internal alkene now, so it will be formed as major. So it will be formed as major. That's it. Okay. So this is how you can decide which is major, which is minor. So this is how you can decide which is major and which is minor in the reaction. Okay, so now till now what we have prepared? We have studied about alkenes, preparation of alkenes using alkyl halides with the reagent alcoholic KOH or NaOH under heating condition. So elimination of halide group and hydrogen gives an alkene. Okay, and when it comes to alkynes, upon treating with PDBaSO4 and CaCO3, which is called as Lindlar's catalyst, that also gives cis alkenes. And with sodium and liquid ammonia bridge reduction, we can give cis alkenes from trans alkenes from alkynes. Okay, the next you can take dihalides, vicinal dihalides. What do we mean by vicinal? Whenever the groups attached here, halogen atoms, if you see, are at 1, 2 position now, so you can call them as vicinal dihalides. So these vicinal dihalides, upon treating with zinc, okay, what happens is X hex removed along with this, halide ions removed with zinc as Zn(X2). Okay, if it is removed as Zn(X2), there will be a bond formation between the two carbons here wherever the halide ions are attached. Okay, so that gives an alkene here. For example, chlorine is there, so you are treating this with zinc dust. Now tell me what happens. This chlorine is removed along with this zinc by formation of zinc chloride Cl2. Like this you will get alkenes, okay, from here. And just look at here, alcohols. What we did for alcohols, we need to remove OH group from alcohol and a beta proton from adjacent side. Okay, that is nothing but dehydration. So dehydration can be achieved by this many reagents. Any of this reagent can be used for preparation of alkenes by dehydration of alcohols. Okay, next cold base electrolysis. You can see here in the last class we have studied for preparation of alkenes. When we have monocarboxylic acid, we will get alkanes from cold base electrolysis. But if we have dihalides, dicarboxylic acids like these on adjacent position like vicinal carbons, so that you can remove CO2, you will get a radical here, you will get radical one more here, and the two radicals will combine to make a double bond. Okay, this radical will combine to make a double bond here. So alkenes are prepared from dicarboxylic acid, vicinal 1, 2 dicarboxylic acid by cold base electrolysis gives alkenes. Okay, now again alkenes and pyrolysis alkenes and pyrolysis produces some alkenes. Here we will get a mixture of products, depends on what type of alkane taken, that will be determines what type of alkene formed there. Okay, now what are the physical properties does this have? Just see here, alkenes first 3 are gases, and from next 4 to 20 are liquids, okay, and above 20 are solid. So first 3 are gases, next 20 are liquids, and after that all of them are solids. Okay. Now dipole moment, what do we mean by dipole moment? You just consider a cis alkene and trans alkene. Okay, like this you consider, or you consider with chlorines. So chlorines are more electronegative now. So now what they will do, they will drag the bonded electrons towards themselves and creating positive charges on carbon and negative charges on this chlorines right now. So now where do we have the dipoles? So those are electrons are above side right now. If they are above side, therefore dipole moment will be like this. Okay, net resultant dipole moment will be like this for cis alkene. Okay, if I consider trans alkene, this side above side, this is below side. So they are exactly opposite direction. No? If they are exactly opposite direction, they will cancel out each other. Dipole moment will cancel out each other. That's why cis alkenes will be having more dipole moment than trans. Remember this. Okay. And when it comes to polarity, cis compounds are more polar than trans compound. What I am saying? Cis generally, these are generalized statements. Cis alkenes are more polar than trans alkenes. Okay. Okay, because see they are polarizing towards one side only, but here they are polarizing in opposite direction, both charges. Okay, so cis alkenes are more polar than trans. Okay, so now melting point. When it comes to melting point, so melting point increases with increase in molecular weight generally for a homologous series. Okay, for isomers, so for isomers, trans isomer will be having more melting point than cis, because if you take a trans isomer like this, so it has a close packing. Okay, due to close packing, melting point of trans alkenes is greater than cis alkenes. Okay, now when it comes to boiling point depends upon their polar nature also. So more the polar nature, more is the boiling point, we can say. So polar nature is more for which one? Cis alkenes having more polar than trans alkene. Okay, next solubility. Cis compounds are more polar now, so they have more boiling point as well as solubility also more for cis compounds because they are more polar. Okay, stability. So remember stability, when stability for isomeric compounds, we can say trans isomers are more stable than cis, because in cis same groups on same side now. If the groups are on same side, there will be repulsions between the lone pairs or non-bonding electrons or electron density on the attached substituents. So that makes to be cis alkenes less stable than trans. Okay, remember this statement also. Okay, so what is the reactivity of alkenes, they will ask. So how can we answer this? Reactivity, more stable alkene, less reactive. Remember what I am saying, more stable alkene, if it is already more stable alkene, less reactive. So what we know reactivity here, how can you answer that? So stability depends on number of alkyl groups attached. See, depends on number of alkyl groups. It means what? If C double bond C is there, to this here we have one alkyl group, like you take methyl group or any group here, that group must contain, that alkyl group must contain more number of alpha hydrogens. More the number of alpha hydrogens, more will be the hyperconjugations, more is the stability. So where do we have here? See, here 4 alkyl groups are there. More the number of alkyl groups, more is the hyperconjugative forms with the alpha hydrogens. So stability is more for this all 4 positions of carbons in alkenes are substituted by alkyl groups. Okay, so tetraalkyl alkene is more stable, then trialkyl alkene, then next dialkyl alkene, and here also dialkyl alkene, and here only one alkyl alkene. This is no substituents. So which is least stable with no substituents. Okay, if this is least stable, if it is least stable, it will try to gain the stability by undergoing chemical reactions right now. So now this will be more reactive. So which is more reactive here? simple ethylene is more reactive than this alkyl group containing alkene. Okay, remember. Okay, just tell me here, I am writing some options. Out of this A and B, which is more reactive, they will ask. How can you answer this? So it depends on number of alkyl groups attached. How many alkyl groups here to these double bonded carbons? This side one, this side one. So it can be stabilized by methyl groups of both double bonded carbons. Here these carbon hydrogens won't participate. Okay, and here you have one hydrogen. So now see, alpha hydrogens here are only one. So only it will be having one and 2. Only 2 alpha hydrogens are there, so it will be stabilized only by 2 hyperconjugative forms. But here you have 3 this side and 3 this side. So it means 6 alpha hydrogens are there. So 6 times it will be stabilized by hyperconjugation. Okay. Next. So now based on their stability, we got to know the reactivity also. So more the number of alpha hydrogens, more is the stability, lower will be the reactivity right now. Okay. So now alkenes will undergo this many type of chemical reactions here. First one is addition reaction, next oxidation, next substitution reactions, polymerization and isomerization. Okay. So now here especially oxidation reactions of alkenes is more important here. Yes, all of them are important, but oxidation reactions are more generally asked in the exam. Okay, more regularly we will be seeing questions from this oxidation reaction, so highlight that. Okay, so now alkenes undergo addition reactions. Addition reactions means, for example, I have the simple ethylene molecule. To this we can add H2. Okay, so this can be, what happens now, tell me. So it will be in presence of metal catalysts like platinum, palladium, or nickel kind of catalyst. So what happens, these 2 hydrogen atoms in the molecule will be added to the substrate. So now it will be giving you CH2, CH2. So here we have hydrogen atoms now. The 2 hydrogen atoms you can add here like this. Like this. So addition of 2 hydrogen atom must take place from same plane when we are using this metal catalyst. Okay. So you can say cis addition it is. What is that? Cis addition. It means both hydrogen atoms should be in same plane. Okay. So now this is what hydrogenation of alkenes for preparation of alkanes. So we have already studied about alkanes preparation. Now same thing is repeating here for alkenes as a chemical property of alkene. Okay. So once someone's preparation method is someone's chemical property, like that. Okay. So it is a preparation method of alkanes and it is a chemical property of alkene, that's it. Okay. And I hope you have watched the preparation methods of alkanes, there we already discussed about this. Okay, right. Now one simple question here you can expect is this kind. Only one equivalent. So one equivalent hydrogen presence of metal catalyst is provided. Now they are saying this is A alkene, this is B alkene. Out of this AB, which alkene carbon, which double bond will be more reactive? Tell me which will be more reactive. How can we decide that? So it depends on the reactivity of this double bond depends on stability. So this is more stable alkene now, so less reactive. This is less stable now, so more reactive. So B will be hydrogenated first, then next A. So reactivity of B double bond is more than reactivity of A. So like this you can expect a question. The next oxidation reactions we have. Okay, oxidation reactions. Before that, addition of C double bond CH2 H2, and to this halogens can be attached, okay, in presence of non-polar solvents like CCl4. So this addition also, like one halogen here and other one here, just wherever we have double bond, remove the double bond and replace with halogen atoms like this. Okay, so now here I am writing so now what happens, one bromine comes here, other one here. Like this. Okay, and you know bromine water I can say, or solution of bromine you can say. So this will be having reddish brown color. What I am saying, it is reddish brown. So whenever you are adding this reddish brown liquid to our alkene, decoloration of bromine water takes place. Why it will decolorize? Because bromine is reacting with this now. So whatever the quantity of bromine is there, that will react with the given alkene. So all bromine atoms or molecules are consumed during the reaction, therefore its reddish brown color disappears, or intensity of that reddish brown color decreases as a quantity of bromine decreasing. Okay, because it will be reacting with this now. So we can say the unsaturation or unsaturated compounds can be identified upon treating with bromine water by looking at the color change. Okay, right. Next, now what will be the mechanism followed is one of the question you can expect here. See, here bromine is there now. So between two bromine atoms, so this bond, whatever the bond is there, this is weak bond. Okay, so that is a weak bond, and you know this double bond of alkene will attacks on the bromine. So this bromide, one of the bromine atom converts into bromide ion, and here creating a positive charge. There this lone pair electrons will goes. Okay, so bromine like this. So you can place positive charge on this bromine now. Okay, and one more bromine atom is there now, which is coming out as a bromide ion. So that will be attacks at one of these carbon atoms of 3-member cyclic ring. Halonium ion mechanism you can say. So bromine here and one more bromine here. Okay, so now what is the use of learning this mechanism? See here, to the same double bond I am adding HOCl. What we are adding? HOCl. This is hypochlorous acid. So hypochlorous acid contains one OH minus ion and one chlorine with positive charge. So chlorine positive charge is electrophile now. So to the double bonded electrons are removed, donated. So chloride ion with positive charge, chlorine with positive charge, these pi electrons are taking. When it is taken, so chlorine becomes neutral, but this carbon becomes positive. At the same time this chlorine lone pair will be given here once after accepting these pi electrons. So that you will get chlorine F 3-membered ring like this. Okay, and the next you have OH minus ion. So this OH minus ion is a nucleophile. So now where it will attacks, at this first position or second position? How can you decide? So just try to open the ring. If you open the ring from this side, you get a secondary carbocation. If you open the ring from this side, primary carbocation. So you just attack it from the secondary carbocation side and gives a compound like OH here, chlorine Cl here. That's it. This is the product form. That is the product formed. Okay, just tell me here. Where you can add HOCl. Okay, so which double bond? Only this double bond will take now. So which side we need to add OH and where do we need to add chlorine? So just add negative part of the molecule to the more stable carbocation side. It means if chlorine atom is going this side, like halonium ion is generated here like this. Okay, so this negative charge of O will attacks this side, because when it is attacking, so during the transition, when it is coming here and it is going out now, here you are getting a positive charge that will be more stabilized whenever there is some stabilizing groups, like stability of carbocations like 3 degree, 2 degree, 1 degree in case of alkyl groups. Whenever you have benzene, you just need to check for the resonating structures. Okay, so it means OH comes here and chlorine comes here. So this is a trans addition. What is this? Anti addition or trans addition. Okay, it means both groups should be added from different planes, above the plane and below the plane, you can say. Okay, right. Next here, addition of hypochlorous acid. So whatever we discussed, like there will be double bond, they will give it as HOCl, I told you. That is nothing but generalizing it as HOX. Okay, it can be HOBr also or HOI also. That's why we are generalizing it as HOX. X means halide. Okay, same thing mentioned in this form, halogen with water, H2. So reaction will be same in both cases, whatever we discussed, like chlorine comes here, OH goes here, that's it. Next one is hydroboration. So what do we mean by hydroboration here? See, we'll tell you one simple trick to remember this. So if the given unsymmetrical alkene is there, so to this we need to add B2H6 H2O2 in basic medium. Okay, this is in basic medium. Now simple hydroboration of alkenes gives alcohols. What it will gives? Alcohols. Okay, so now where do we need to write that alcoholic OH group to this double bonded alkene? So now just remove double bond and we need to insert OH group. So how many carbons are there? 1, 2, 3 now. So write 3 carbons as it is. After writing 3 carbons, here you can add OH or else you can add OH here. So but where do we need to add properly? That is what the main question now. So here whenever there is unsymmetrical alkene, hydroboration takes place and generates OH group at here and hydrogen atom at here. Okay, so we need to convert given alkene to alcohol. So during this process, no rearrangement, nothing takes place, just wherever you have double bonded carbons, that will be the reactive side. So less stable less substituted side of the alkene carbon converts into OH group. Okay, so this is the only thing. And the next one, okay, so based on yesterday's discussion, you can solve this question, and today's and yesterday's discussion, you can solve this question and this question also. This question also as homework I am giving. So just try this, and if you have any doubts, just mention in the chat box. I will be explaining in the upcoming session. Okay, that's it. Okay, this is about the session. So thank you for watching. Stay connected with our NEET World channel. Thank you.